Welcome back, viewers. We are beginning with the new playlist related to the first year subject of VTU affiliation. It is Basic Electronics and Communication Engineering. We will be beginning with the first module. The name of the module is Electronic Circuits, and this module is divided into four chapters, namely power supplies, amplifiers, operational amplifiers, and oscillators. So as per the syllabus, we shall begin with the first chapter of the first module, that is power supplies. So in this chapter, we will be studying following topics. There's a block diagram of a power supply, rectifiers, reservoir and smoothing circuits, full wave rectifiers, the two types of full wave rectifiers, that are biphase rectifiers and bridge rectifier circuits, voltage regulators, and in order to learn these voltage regulators, we will also be studying its output resistance and voltage regulation. And lastly, we will be ending the chapter by discussing about voltage multipliers. So in the slide, you can see the block diagram of a power supply. Normally, the voltage what is available to us at a household or industry is alternating, and the current which we get from the alternating voltage is called as alternating current, and in general we call it as AC. Now what we get at our now local plug points is 240 volts AC. Intention here is to get a DC output which may not be 230 volts. It may be 48 volts, it may be 24 volts, it may be 12 volts, it may be 6 volts, or it may be 3 volts as per the applications in the DC circuits. Now how this 230 volts AC is converted to the said levels of the DC voltage is briefly explained by this block diagram. Let us see what are these blocks step by step. A high voltage AC is applied as an input to the first block, which is the step down transformer. The function of the transformer is to give the isolation between the primary and secondary, so there will not be any electrical contacts, it will be magnetically coupled. Now in this transformer, the step down type of transformer, the secondary voltage will be less than that of the primary voltage. So that means now we get a reduced voltage, but still it is in alternating form, which cannot be called as DC. So this reduced voltage or the low voltage AC is connected to the rectifiers. Function of a rectifier is to convert AC to DC. Now if we give a sinusoidal voltage as an input to the rectifier, we get a DC voltage which is still not a smoother version. It will be a unsmooth DC. So in order to smoothen this unsmooth DC, we are using the smoothing filter or a reservoir. But still, we will not be happy with the output what we get. Even though this is a smooth DC, there will be ripples in the output, and this ripples will be further nullified by a circuit called as a voltage regulator, and thus we make an attempt to get a regulated fine and smooth DC from the high voltage sinusoidal AC. Here is a symbolic representation of the same block diagram. Electrical symbols are shown instead of the regular names. The symbol stands for the transformer, and this is a symbol for a bridge rectifier. This is a symbol of the capacitor which indicates a smoothing filter, and this is a transistorized regulator, or this is a regulator based on Zener diodes. So this is about the block diagram of power supply. Now, as per the syllabus, we shall study these blocks in detail, that is starting from the rectifier, what are the types of rectifiers, and each rectifier circuit type has its own smoothing filter, And once we cover with the rectifiers and their subsequent smoothing filters, we will be going towards the voltage regulator. That explains this entire block diagram in detail. So let us see about the rectifiers. Rectifiers can be classified into two types, that is half wave and full wave rectifiers. And in full wave rectifiers, we can further categorize them into two parts, that is biphase rectifier and bridge rectifiers. We shall see about these types of rectifiers, half wave and full wave, and in full wave, biphase and bridge. Let me repeat the definition. Rectifier is a device which converts AC to DC. So we shall be proceeding with the rectifiers. So here is the simplest circuit shown for a rectifier. It consists of a transformer, it consists of one diode, and it consists of a output terminals. This is called as a half wave rectifier circuit. So the mains voltage what we are applying, it is shown as 240 volts, but it can range anywhere between 220 volts to 240 volts, because the MESCOM or the KPTCL supplies what we get will have a slight fluctuations in them. So this voltage is applied to the terminal of a transformer which is called as primary. Now as discussed in the block diagram, this is a step down type of transformer. So the secondary of this transformer will give us 12 volts. Please note that this 240 volts and 12 volts are RMS values. So I am giving a assignment to my viewers. Find out what is the relation between the peak value and the RMS value. So I hope you know that equation. By assumption, we shall proceed. So the secondary of this transformer gives us 12 volts RMS, and still the input here is AC. Now this 240 volts is converted to 12 volts, and thus the turns ratio of this transformer will be 20:1. So that means every 20 volts in the primary will be equal to 1 volt in the secondary. This turns ratio is a very important factor in transformers. Now we can see in the diagram that this circuit consists of AC which may have two cycles. In general, if you want to draw a AC waveform, it will look like this, and we call it as positive half cycle and negative half cycle. Let us analyze this circuit with respect to positive half cycle first. So if I am applying a positive half cycle initially, okay, if I am initially applying the positive half cycle, then this will be the type of the waveform what I am applying. This will be the positive terminal and this will be the negative terminal. Let us see what happens to the diode. The positive of the supply is now connected to the P side of the diode, and negative of the supply is connected to the N side of the diode via load. This creates a forward bias in the diode. So if the diode is forward bias, we know that it acts like a closed switch and it starts conducting. So if the diode conducts, then it is no longer an obstacle, rather than it will be a closed switch completing the circuit. If that is the scenario, then we can see that current in the circuit flows in this direction which is shown. Now let us analyze a similar scenario with respect to the negative half cycle. With respect to the negative half cycle, what happens is this diode direction will be reverse biased. So in reverse bias condition, the diode will no longer act like a closed switch, rather it will act like an open switch. So if it is an open switch, there is no physical connection between this input and the output, thus the output voltage will be 0. Let us try to understand this better with the help of waveforms. So this is the secondary voltage which is 12 volts in the diagram, and as mentioned a while ago, this is the RMS value. And I told you guys to find out the relation between the RMS value and the peak value. The peak value is root 2 times the RMS value. Thus, we get it approximately 16.97 with respect to 12 volts, which is equated to 17 volts here. And this diode is made up of silicon or germanium, which will have a drop of 0.7 volts. Thus, we see that the output voltage will lose 0.7 volts from the input. So, input has a peak of 17 volts, thus output will have a peak of 16.3 volts. And we see that during the negative half cycle, the diode is reverse biased, thus it will not conduct, and hence in the negative half cycle of the input, the output voltage will be 0. Now we see that only one half cycle is retained and another half cycle is lost, and the scenario repeats in all further subsequent cycles. So since half of the cycle is lost, we call such type of rectifier as half wave rectifiers. So a numerical example is shown here why those values in the waveforms were equated to be these volts and diode drop is shown. Let us take one more example to understand this better. In this example, let us try to understand the question. The mains transformer having a turns ratio of 44:1 is connected to 220 volt RMS main supply. If the secondary output is applied to half wave rectifier, determine the peak voltage that will appear across the load. So in this question, the transformation ratio or the turns ratio of the transformer is given, and it is said that the supply is 220 volts and it will be stepped down with respect to the output as per the requirement which is given. Thus, we have to find out what is the voltage that will appear across the load. Now here, I will not be making the numerical substitutions. I am leaving it to you guys. Please take out your calculators. If necessary, pause the video in between and complete this numerical example. So once again I repeat, you will require the help of the calculators to solve this. So I shall not be solving the numerical values. I am leaving it to you guys. I shall be only mentioning the method. So here, the secondary voltage is the primary voltage divided by 44 because the turns ratio is 44:1. And we know that primary voltage is 220 volts. So calculate the secondary voltage. It will be 220 divided by 44. So I hope you have got this value. With this, we shall proceed. Now, the relation between peak value and RMS value is given by this particular formula. The value what you got for the Vs is the RMS value, and I am interested in finding its peak value. That is the peak value of the secondary voltage of the transformer. Please calculate. So once we have got the peak value of the secondary, let us assume that in this half wave rectifier circuit, the diode voltage has a drop of 0.6 volts. It can be anywhere between 0.6 and 0.7. I am assuming it to be 0.6 volts. Then the peak voltage that appears across the load will be the supply peak minus this 0.6 volts. So the load voltage will be the peak voltage of the secondary RMS value minus 0.6 volts. Kindly solve. So I hope you guys have got the answers for this. If not, please pause the video, rewind it and watch this part again. So further, we will be proceeding with the reservoir and smoothing circuits. We know that the half wave rectifier, half of the cycle is lost and only half of the cycle voltage is retained, which is not smooth. So there is a discontinuity in the output, which is not liked by most of the electronic circuits. In order to maintain the continuity throughout from starting to the end, somehow we have to smoothen the output voltage of the half wave rectifier. In order to overcome that, a reservoir and smoothing circuits is introduced. What exactly this reservoir and smoothing circuit does is, reservoir stores the energy and smoothing circuit smoothens this waveform. Here we see that only one capacitor is added to a half wave rectifier circuit, and it will do the necessary job for us. How exactly it does, that we shall see with the help of the waveforms which is shown. What exactly happens here in the output is, the in the forward bias condition the capacitor charges. In the reverse bias condition, the diode is open, but the energy stored in the capacitor is given to the load. Thus, we will not be losing the negative half cycle. The dotted lines here shows us the output of this half wave rectifier without capacitor, and with the capacitor the output is shown by a solid line. That is, in the reverse bias condition, whenever this peak voltage reduces, the input reduces than the peak voltage, the capacitor which is fully charged up to this peak voltage value starts discharging. Thus, we get a smoothened waveform. And if there is any difference between this point and the peak, we call it as ripple. As an engineers, it is necessary to maintain this ripple as low as possible. And still, if we are not happy with the output what we get from the smoothing circuits, we can go for additional stage of smoothing circuits by adding one extra resistor and one extra capacitor. It comes with the added cost. So what happens here is, this R1 and C1 will act like an impedance potential divider, and thus C2 will filter out the remaining harmonics or the ripples. So the by what factor the ripple reduces is given by this formula, that is xc divided by root of r square plus xc square, where r and x are the impedances of these two components respectively. It indicates that we can add as many capacitors as we want in order to get smooth and smooth waveforms, but like I said, it comes with the added cost, and added cost is the capacitor requires energy to charge and it will be drawn from the supply. So thus, for a very small instant of time for the capacitors to charge, a very large value of current will be drawn from the supply, which is not acceptable. It causes the surges and thus it may damage the transformer also. So maximum 2 capacitors can be allowed in the practical circuits. Let us see by what factor this ripple reduces. Here numerical example is given. A RC smoothing filter in the 50 Hz means output, the resistance consists of R1 is equal to 100 ohms and C2 is equal to 1000 microfarads. If 1 volt is the ripple across the input of the circuit, determine the amount of ripple that is appearing output. So what is given here is the value of this resistor and this capacitor, and using this formula we have to see that what is the amount of ripple reduction. It is said that if these two components were not present and only if C2 was present, then in that case the ripple what is shown here is 1 volts. So as per the numerical, the ripple is 1 volts. So we have to calculate it using that formula. A simple substitution, a direct substitution in the calculator will give us the answer. So I am showing it to you. First we have to find out xc, which is given by 1 by 2 pi fc, and frequency here is 50 Hz. 2 pi is 2 times 3.14, but please don't use 6.28. Kindly use the pi option in your calculator to get the accurate values. And capacitor is 1000 microfarad. So micro stands for 10 to the power minus 6. Since this is a very large term in the denominator, kindly use the brackets in your calculator. You should get somewhere around 3.18 ohms for xc. Once we get the value of xc, we have to find out by what factor the ripple is reduced. In this formula, we substitute all the parameters accordingly, and we see that the 1 volt ripple is now 32 millivolts. So just by addition of one extra resistor and one extra capacitor, the ripple is reduced drastically by a variety of major factor. So that's all we have got in this video. In the next video, we shall learn about full wave rectifiers and its filters. Thank you.